All right, so a couple comments picking up from last time. Actually, before I start, if either Brittany or Hovar are here, come find me afterwards. Just a couple administrative things I need to talk to you about. So one thing that might have been confusing from last time is the following. So I talked about using wildcards to basically indicate groups of files, and that you can use syntax like this, and we saw a couple examples of this. So that's quite useful for when you want to sort of choose some set of files. I also talked about this Unix utility or command called grep that will allow you to find patterns within files. So one thing that might not have been obvious was that the sort of syntax for finding patterns, so here's a pattern, here's a pattern, here's a pattern, all of these are being passed into grep. The syntax here is different than the wildcard syntax. Some of the things look kind of similar, but it's not exactly the same syntax, so I just wanted to make that clear. And this syntax is starting to get into something called regular expressions, which we're going to do in a lot greater, more gory detail from within R. We're not going to do a lot of it here from within Unix. But this sort of pattern syntax that you see here is going to be useful for problems 3 and 4 on the problem set. And I don't think I'm working through sort of formal solutions right now. You're not going to need to do anything really fancy or complicated in terms of these patterns and regular expressions on the problems for the problem set. And I'll also, there are a couple things that I realized were a little bit more tricky than I had thought. So I'm going to send out a few more hints for for those problems 3 and 4 probably today. Okay, so let's pick up where we left off in terms of redirection. So I said that we can basically Unix commands are often taking input from input and sending output places. And the idea is we can control where it takes the input from and where it sends the output to. So in general, by default, there are many of these Unix programs are just going to take it from something called standard in, which is just what you type at the keyboard by default. And they're going to send it to what's called standard out, which is just going to show up on your screen. But if you don't want it to come from your keyboard and you don't want it to go out to just print it out to the screen, you can control where stuff comes from and where it goes to. And that's this syntax up here with the greater than and the less than sign. So you can basically send you can get input from a file and you can send output back out to a file as opposed to using using the keyboard and as opposed to writing out to the screen. So if we want to see an example of that, oops, wrong thing. So I'm just going to jump ahead slightly here. So here's an example of doing that, of running some MATLAB code in the background. So not starting up MATLAB and typing at the command line, but running the code in this file of MATLAB code. So here's how you invoke MATLAB from the command line. Here are some flags that we can pass to MATLAB, just like those other flags that we were passing to things like tail or grep or some of the other Unix commands. And here this is saying run MATLAB using the code in this simulate.m function and pass any output that would normally be going to the screen, pass it to this file that is called simulate.out. And we'll see this in a few minutes. This says put the job into the background, so don't occupy my terminal window. Put it in the background and allow me to keep typing other commands after you start up this operation. So that's an example of using of redirecting standard input and standard output to other places that are useful. Okay, so in addition to redirecting stuff to and from files, we can also redirect stuff to and from other commands. So this is really where the power of Unix and the shell comes into play. So we've already seen that there are a few really helpful utilities. Those were in this previous table here. You can see there aren't that many of these. These are basically the ones that I know reasonably well. There are a few others, but these are basically the ones that I work with sort of on an everyday basis. And so the power of using the shell and of these commands comes from combining these different operations in creative ways. And if you combine these different operations, you can do a lot of really fairly sophisticated sorts of things. So these are all the commands that are basically the sorts of things you're going to be needing for the problems on the problem set, and you're going to need to combine those commands in different ways to be able to solve the problems. So let's see an example of doing that. And one of the main utilities we're going to use in terms of combining things is this thing called piping, and using this this pipe symbol. So the basic idea is instead of redirecting output to a file, you can redirect output as the input to another operation. So let's go over to the demo code and actually see this in action. Okay, so we've seen that we can redirect output into a file. That was this example here. But I can also redirect output using this pipe that passes stuff from one command to another. So here's a pretty simple one. I'm just going to take the result of doing an ls, which will list out files, and I'm going to pass it into the head command. And the head command basically just is going to take the first x number of things and show that. In this case, with the -5, it should show the first 5 things. So instead of LSing out all of the files, maybe I have thousands of files in my directory, this would just show me the first 5. So you can see, indeed, that's what it did. If I had just done ls, it would have shown me all of those. If I do the ls with the head, it just shows me the first 5. Okay. So that was fairly straightforward. I'm just passing the output from one thing into the output from one thing as the input to a second thing. But we can start to do this where we're passing from one thing to another thing to another thing to another thing ad infinitum, sort of as long as we would like. So here's an example of that. So this mileage2009.csv is in the Git repository. It's in this lectures directory. If we just look at it with the less command, we can see what it looks like. It's basically a comma-separated data file. It's some information on cars and mileages and engine sizes and things like this. There's a header row that says what the names of the different fields or columns are, and then there's a record for each of these different kinds of cars. So one of the sorts of things, this is not a very long file, but in practice what you often end up getting, so if I just less through this, well, that's not entirely short, but this is probably some hundreds of lines. In practice, we might be dealing with data files that are thousands, hundreds of thousands, millions of lines, and we're going to need to be able to filter those files fairly quickly in terms of rows and columns. So instead of reading it into R or reading into some other program, we can just do that filtering at the command line. So here's an example of doing that. So I'm going to use the cut command. That is basically used for extracting columns. I'm going to say cut up this CSV file into columns with the delimiter of a comma. So that's going to separate that's going to be the field, the symbol, the character that separates columns in the file. And then pull out the second column, the second field. F is for field. So that should give me just a single column, all the values of what's ever in the second field. And then I'm going to say, well, maybe I want to sort that. So I'm going to pipe the result from this first command into sort. So usually sort would take its own input, but here we're saying pass the result of the output of this into sort. And then I'm going to pass this into unique, and that's basically going to remove any lines that are repeated. I need to do the sort before the unique, because unique only works by removing lines that are repeated when they're next to each other, adjacent to each other. Okay, so that's fine. And then I'm going to pass that into another Unix command called WC, which counts up the words. So this is just going to basically, the whole result of this operation is basically counting up how many unique lines there are in this file. So we can do each of these things we could run through them, each of them individually. So if I do this, indeed it prints out this second column, which happens to be, it looks like the name of the manufacturer of the car. And then if I do sort, actually this is not very exciting because it looks like this is already sorted. But obviously in many cases things won't be sorted. So you can see this is now indeed sorted alphabetically. And if I do unique, well, that should get rid of all the extra VWs and Volvos that are in there. So that's pretty helpful because now I can just see what's the complete set of manufacturers that are in this data set. And that's going to give me that list of unique values. Looks like it also grabbed some stuff from the header row as well. We could have removed that using head or tail initially, but in this case I didn't bother to do that. And now if I pass that into word count, it says, oh, there are 50 lines, 56 separate words, 416 separate characters. So that's kind of useful to know. That might be something that we might need to know as we're doing some pre-processing and getting a sense for some data set that somebody sent us so that we've downloaded. If I instead wanted to actually number the lines, I could just pass it into a different utility. So if I do pass it into this NL utility, which numbers the lines, you can see it's just putting a line number in front of each of those. Okay, so we can mix and match things here to do different sorts of things that we're interested in. Questions, comments about this?
What does the minus D do?
The minus D says what's the delimiter, what's the special character that marks off one column from another column. Yeah, so sometimes you'd get a file that's separated by commas, sometimes it would be separated by tabs, sometimes it's separated by other things. If I wanted to separate it, if it was separated by tabs and I wanted to tell it that, what we'd usually do is something like this. So the slash is basically an escape character, and that this is a special character for saying a tab. Other questions? Okay, so this is sort of this, what I just said in the last few minutes is basically sort of the fundamentals at the heart of doing stuff in Unix, is that this idea of we've got these individual utilities that are specialized to do very particular things and do them very well, very modular. We combine them together with piping, and that allows us to do much more sophisticated things. Here's another example. This is a real life example that I used a couple years ago. I'd gotten a whole bunch of files of climate data, and in the files there was information on precipitation and temperature and stuff from different weather stations around the world. And they have a whole bunch of codes of basically whether the data are reliable or not, or something weird happened with the data collection on a particular day. So for some reason or other, I was interested in seeing if there was this particular code S in the file, in any of these files. So I just did it first on an individual file. I said cut. The minus B, unlike the minus D, will cut basically by character. So this is pull out the first character from each line, the second character, the third character, the 11th character, the 29th character, the 37th character, because those are the particular elements of the file that I was interested in. Pass the results of doing that cutting into grep to look for this capital S, and then pass that into less so I can look at the lines that have an S in them. So I was just trying to filter through and look for the places where this character came up that indicated something wrong with the data. And this should work here because I think hopefully I'm in the right directory here. So you can see it is indeed giving me the results of the lines that have that information, and that was useful to me. It was particularly useful to me when I combined it with actually using wildcards. So I said, give me all of the files that start with USC, have anything in the middle here, and then end in period DLY. These are all basically all the US stations. And I'm again looking for this capital S, and I'm passing it into less so I can see. So there are literally thousands of files that look like this in this directory, and if I were to sort of read those into R, or read them even into a faster program, to basically look for stuff, it would have taken me hours. And when I did this, it took me a few minutes to just process through directly in Unix. Yeah?
Suppose the file is too big to load into the memory directly, then would it slow down the...
It's not getting loaded into memory. It's basically reading it in. It's basically streaming it from the file, reading it into the program, and then passing the output through. So it's not reading everything into memory all at once, which is in part why it's quite quick compared to trying to read the file into memory once each for all of these thousands of files. So this would actually take a few minutes to run if I do it. I'll just start it and see if anything interesting happens. So it's basically just processing through these files, and it's not showing anything because it's not finding any of the S's, which in this case was what I wanted because I was hoping that those characters didn't show up. So this is basically sort of a quality control check on my part. I don't remember how this finished or exactly how long it took, so I'm going to hit Control-C and then hit Q and get out of that. But that's an example of combining things together. Okay, so we can also, so here's another example of combining things together. I'm going to go to this directory where in the Git repository for the class where I have these shell files. Remember, I've got the various files that have shell code in them. So here's just another sort of example of this. This does, here we go. So the minus L, we've already seen spit stuff out in long format for LS. The minus T does it in order of what's been modified most recently, so that's pretty useful to be able to see what are the files you've worked on most recently. Looking at all these files ending in SH, I'm passing into head -3 to get the 3 that were modified most recently. So these are the 3 SH files that were modified most recently. This is not surprising. This is the one that I'm showing you today, so that's the one that I've been working with most recently. So another way to pass information is, in some cases, a command is not looking for getting information from standard input or standard output, but is just looking to get, is just looking for the information, the input, as basically an argument. So this is another syntax. These backticks are a way to take the result of one command and also use them as input to another command when that other command is just expecting input as one of its regular arguments. So here what I'm doing is I'm saying, okay, I want to grep for the pattern FOR, so I'm looking for for loops, in any of these shell files, but only those first three that I've modified recently. So maybe I'm just looking for where the appearance of a for loop is in some of the files that I've working on recently, so I could do it this way in order to pass in just the files that I'm interested in to use with the pattern searching. So if I do that, that should reveal that they're what did they do there? Sometimes with backticks and quotes, it's a little weird when you copy from one program to another. So let's get rid of the backticks and see what. Oh, I see what's happening. Okay. So if I do this, it is. I did it in long format, so it's printing out all of this, but then I'm passing that into grep, and grep is just expecting the names of files. It's not expecting all of this other extraneous information about the files. So I need to take out the -L part of this. So if I take out the -L part and just leave the -T. Oh, as a side note, I did -L, -T. I can also do -L, or I did -LT, and that's equivalent to doing -L and -T. Either way is fine. All right, so I just want to do the ls -t, and now let's wrap that inside the, okay, so that worked. And let's actually do the color bit so we can see it a little more easily. So if you remember from last time, I think that worked, yeah. And also, let's then pipe that into less so that we don't get too much output printing to the screen at once. Looks like I lost the coloring, probably because of some interaction with using less. So now you can see, okay, here are the files where for appears. Okay, here's the for, here's the for, here's the for, there's the for, etc., etc. So I'm able to sort of do these somewhat sophisticated queries by combining things together. Okay, any questions? Yeah.
Is it possible to display that which line in that file?
Yeah, I'm sure it is. That would probably be an option to grep. So let's see if we can quickly look through here. Actually, this is a good opportunity for me to say something I'd been meaning to say, which is you're going to need to use man to try and look up different flags and options for these different utilities as you're working through doing things in Unity, in particular on the problem set. There's going to be a lot of stuff in here that's going to be hard for you to figure out. Like even when I look at these, I'm like, there's oftentimes some very technical details. I'm like, I don't understand that. I don't know what's going on with that. And so it's just you just sort of need to develop the skill to sort of find the useful stuff that you need and ignore all the sort of extra technical stuff that you don't need. So we might, if we spent a little bit of time, be able to figure out what we could use to include line numbers in here. I'm not sure. That looks like there's something about line numbers here, but maybe not quite what we're looking for. Dash n. Okay, so if you know what you're looking for, it's really easy to find. Each output line is preceded by its relative line number in the file starting at 1. Okay, so if you have a friend who can help you, that's even better. So it looks like we can do grep. This color wasn't working, so let's just take that out anyway. Okay, so now you can see it plugged in here, some additional information that's this line numbering. So if you manage to come up with a question like, can I do this? The answer is almost always or usually yes, because as you can see, all of these commands have zillions and zillions of options. And if you've thought of it, somebody has probably thought of it before and may have very well have put in some functionality to do that. Okay, another thing we can do, and this is getting a little bit ahead of myself, but it's sort of in the same theme, is we can pass the result of running a command into a shell variable to store the result. So we haven't talked about shell variables, but we will in a second. So what this does is it says take the output of ls and store it in a variable called files, and this is the syntax to be able to do it. You put a $, which is usually used to refer to variables in bash, and then the parentheses just sort of sets things off to let the syntax work. And then I can say echo and then the name of the variable with the $ in front of it and see what's being stored in that variable that just got created. So if I do that and then hit there, okay, so it doesn't show anything, it just stored the variable. But then I can do echo files and it'll show me what's stored in the variable. So you can see it's just the names of the files separated by spaces. So we could then actually do some processing on that variable potentially to then to then further do some other stuff down the road.
What's the lifetime of that variable you define?
Yeah, so in general, the variable is going to disappear if you close the terminal. We will get to that a little bit in more detail in a few minutes. Okay, so let me say a little bit about controlling jobs. So if we start to run a command or run a program in Unix, there are some various things we can do to control how long it runs for and basically get a sense of what kinds of, how much resources it's using. So here's an example of, let me just, so I'm just going to start up R from the command line here, and I'm just going to start an infinite while loop just for the sake of being able to see how we can. So basically, in lots of Unix commands, we can hit Control-C to interrupt the execution. So you can see this just interrupted that infinite while loop and put me back at the R command line. If I restart it, I just did a up arrow to this works in R as well to get back my previous command. If I hit Control \, that's usually going to kill me out of the whole command, so that returns me to the Unix prompt. So Control-C and Control \/ are both useful. We've already seen this about redirecting input and output. So now let's do an example. Let's see an example where we're actually able to see all of the different stuff that's operating on a machine. So I'm going to SSH to Arwin, which is one of our servers on the SCF where people are often running jobs. And I'm going to use a new command that we haven't seen called PS. And this basically prints out information about all the jobs that are running on a machine. So you can see what job you have running. You can see what other jobs other people have running. Get some idea of if the machine is overloaded with lots of people using it or if it's fairly free and there are going to be resources for your job. So this PS -AUX will basically print out a whole slew of information on all of these. So again, I could do that. I could do that with less. Oops. So this shows that Unix is waiting for some more stuff. Okay, so this just shows the top, which is just showing a bunch of system stuff. So if I start paging down, I could start to see if there's anything maybe more interesting than just system stuff. It looks like one of the grad students, Adam, looks like he has a few things running. That's 6 or 8 lines down there, and we can get a sense for what's going on. So for some reason it didn't like my syntax. I'm not quite sure why. Okay, so one thing I'm going to ask you to do, I'll send out a post on Piazza soon after class. I'm going to ask you to explore some of the arguments to PS and see if you can do a couple things with PS, and I'll ask you to do that just as an informal homework problem for Monday. So I'll give you more details in that actual post, but you'll sort of play around with being able to use man to see what some of the arguments are and being able to apply that on one of the SCF machines. Okay, so that, I guess I should have also pointed out that what's really useful in this, in addition to all this information, is it shows who the users are. It shows what the process ID is, which is going to come up and be useful in a second. It shows what percentage of CPU is being used. So if it's a job that's really active with CPU, it's going to show generally 100%. It shows what percent of the memory on the machine is being used. And then there's some other stuff that I actually don't remember what all of this stuff is. It shows when it started, and this is probably how long it's been running. And then it shows the command that was used. So that's all useful to know. The next thing I'm going to do is actually run a fairly intensive R job, and we're going to be able to see that we're going to be able to see how much it's using in the way of resources. So I'm just creating a file of R code using echo. So I'm basically rather than creating an R script file by actually typing in these commands, I'm just doing it from the command line by using echo and passing that in by redirection into the file. And here I'm doing appending as opposed to this will overwrite it if it already exists. So let's go ahead and create that file. So I'm basically just creating the file temp.r. Okay, there it is. It's a big for loop that creates a big matrix and does a big linear algebra operation. And the whole goal of this is just to have a big job that's running and using a lot of resources so we can see what it looks like when that's happening. Okay, so I'm going to go ahead and run that. In general, there's this command called nice that will basically let users share resources on the system, say in such a way that you don't interfere with other users. So this basically puts jobs in a lower priority. By default on all of our compute servers, you don't need to do this because it already is going to put them at lower priority for jobs that are appropriate for jobs that are running in the background and that are longer term background jobs. But that is the syntax if you want So if I, ignoring that for the moment, here's how I would submit a batch job in R to do operations in the background. What this does, actually, let me, I'm going to kill that job. So I'm going to do kill. This 17446 that it returned to me is the process ID that I can refer to the job by. So I'm going to kill it. So it says, oh, indeed, I terminated that. If I had done this, you'll notice it doesn't come back and give me a prompt anymore, unlike here. And the reason is it's not put the job in the background. It's still sort of sitting there running in the foreground. And it doesn't allow me to keep working and doing other things. So if I had either done the ampersand, that'll put it in the background. Or if I'd forgotten to put the ampersand, I can now do Control Z. That says, oh, it's stopped, but it hasn't been terminated. It hasn't disappeared. It's still sitting there waiting for me to tell it whether to do something or not. And if I hit background, if I type BG for background, it'll put that job in the background. So this should now be running based on this sort of intricate sequence of commands I just entered. So that R job should now be running. And if we could use PS to see what the usage is, but what's usually more useful if we want to try and get a sense of resources and who's competing for what on the machine is to use a command called top. So I just typed in TOP. And that will show me basically all the stuff that's running intensively. And it'll basically show me fields with information about each of the jobs. Yeah, question?
I was wondering, it didn't look like it gave you when you put it into that, it didn't look like it gave you one of those ID numbers. I was wondering if there's any way of seeing that.
Yeah, I'm not sure. Usually I just use the ampersand and then it'll appear as opposed to the Control Z in the background. And oftentimes it'll just be obvious because you may not be running much on the machine. You can sort of look at this and decipher what was the job that just started. Yeah, question.
For the top job that's running, how is CPU usage greater than 100%?
Yep, that's one of the things we're going to get to. So what can we notice here? Okay, so it looks like I've got a couple jobs that are running. I must not have killed a job because I didn't realize I had 2 R jobs running. Here's the command that was used to start the job. It looks like this user p.luke also has another R job running. A couple things we can notice here. His job is using a lot of memory. There's something like 64 gigs of RAM of memory on this machine, and he's using about a quarter of it, which is a bit much for an individual job, but not too terrible, I guess. And then you'll notice that I've got these couple of jobs running, and as Kaushik just asked, what's the deal with the greater than 100% CPU, right? That seems like it should be impossible. So the reason that's not impossible is that this machine has 32 cores on it. Basically, it's 32 separate CPUs on it. And we've set up R. We're going to talk about this a lot more when we get to the unit on R. But we've set up R to, whenever it does any linear algebra, to use something called, to do threading, which basically is going to use multiple cores, multiple processors to do the linear algebra operations. So the reason it says more than 100% CPU usage is this is indicating that R is doing those linear algebra operations that I indicated in my file of R code. It's doing those on multiple cores. It's basically splitting up the calculations and doing some of them on one core, some on another core, some on another core. So in this case, it's using about 5 or 6 of the cores. And you can also see here in terms of this PR and the NI fields what the priority is for each of the jobs and what the nice level is, which are basically have a one-to-one correspondence. So remember, we set up it, we ran it so that it ran at a nice level of 19. p.luke's job is also running at 19. Basically, any jobs that get submitted are going to be running at 19. They're not system-level jobs. And then the priority level is the nice level plus 20. So a priority of 20 is the basic default level. A priority of 39 is actually lower in priority than the priority of 20, even though the numbers go up. And so yeah, you can sort of see that happening.
Chris.
Yeah.
So yeah, see, when you do 90, you do negative 19, and if you do positive 19, that would be like.
Yeah, that would be giving it even more priority. You probably wouldn't be allowed. The system probably wouldn't allow you to do that because it's set up so that you as a regular user can't give yourself very high priority.
So there's no difference.
Yeah. So you guys don't need to. I mean, if you're on our system, you don't need to worry too much about the nicing because that should get set by default. If you're on some other system, the administrators there might ask you to set to use nice whenever you submit a job.
Where we do re-nice the positive and negative side.
Yeah, you can also re-nice. If you start a job and forget to nice, you can use something called re-nice, and the demo file has the syntax for re-nice. And whether you use plus or minus, it sort of goes in reverse and is not always intuitive. So
there's no difference when we do plus and minus.
Well, there is a difference. You can go higher than 20 or lower than 20, But just look at the syntax of the demo file for what you should do as a regular user.
Oh.
In one case, when you use nice, you either need to use minus, and then renext you need to use plus, or maybe
Yeah,
vice
that's
versa.
what I found.
Yeah, so it's confusing. I'm not sure if there's rhyme or reason to it, but if you need to look it up, it's in the demo file for you to look up. But you shouldn't need to worry about it too much. From within top, I can actually kill off jobs. If I hit K, remember before I said kill space and then the process ID? If I just hit K within top, I can just give it the process ID of the process I want to kill. So I can kill off this job. If I hit 0, that's sort of the default, and that will generally kill off the job. Looks like that didn't work. Sometimes there's a lag because the job is sort of deep embedded in the computer in some vague sense and is not able to sort of pull out gracefully very quickly. Let me try and kill off this one. If you really want to kill it and it hasn't died, even if you've asked it to die, you can give it a signal of 9, and that will often do a better job of killing it. Okay, so that did kill that one. I'm going to kill off the 174501. I'll do 9 here as well. Okay, so that did indeed kill off all my jobs. So if I hit Q here, that'll get me out of top. Okay. So one thing about memory usage is if you do see a job, your job or somebody else's job, that gets up anywhere close to 100% memory usage, even if it gets up to like 70 or 80%, that's generally a very bad sign. And the reason it's a bad sign is that when Unix will continue to allow your job to run, even if it starts to approach the physical hardware limits of the memory on your machine. But what it will start to do is instead of actually using the physical memory, it'll start to use memory it'll basically use memory on the hard disk instead of on the physical memory. And when it does that, when it has to use the hard disk and starts copying stuff onto the hard disk, it slows down. And it slows down so severely that usually if you start getting into that situation, it's called swapping or paging. And your job will basically slow to a crawl, and oftentimes will essentially take infinitely long to finish. So you want to, if that's the case, you need to either find a machine that has more memory, redesign your job to use less memory, figure out another algorithm to use that doesn't use as much memory, those sorts of things. We'll talk more about this when we get into talking about programming in R. But that's a general thing about jobs on systems, regardless of what program it is. Yeah.
Yeah, I was just wondering, how much faster would most of the SCF machines be compared to your standard laptop? Are we talking like significant time savings for using just 1 or 2 cores, or is it really only into threading?
Yeah, it's probably not. If you've got a reasonably recent laptop, it's probably not going to make a huge difference. So basically, one of the advantages of using SCF machines is we have lots of cores available, so you could be running more than one job, or you could be running a job that uses more than one core at once. And so that's basically sort of parallelizing by going across cores. The other thing is we have things set up. We have it set up so, for example, R will do threading with the linear algebra, and R uses a very fast background linear algebra package, which might not be set up on your particular laptop. So in some cases, there might not be a big difference. In other cases, you could see an order of magnitude difference if, for example, your laptop is not set up to do fast linear algebra, but you're doing linear algebra in your operations. And that's the sort of thing where it's just basically trial and error. You try it on your machine, you try it on the SCF machine, and you get a sense for how long it takes. Okay, were there other questions? I'm not going to say too much about aliases. Aliases are basically a way to give yourself shortcuts for commands that you execute a lot. So for example, these are some of the aliases that I use a lot. I have an alias Q that stands for exit, because whenever you want to exit a terminal, you would say exit, but I get tired of typing exit because I'm really lazy. So instead, I just want to type Q. And so if you have this command, that will then just allow you to type Q. And if you want this to be available to you, if you want these aliases to be available to you whenever you open a terminal, you can basically include code like this in a file called --rc that you will see in your home directory. So if you look here, this is what's called your bash resource file. And you can include anything in here that you want to be available to you in any terminal that you open on the particular system that you're on. So you would need to do this in your bash RC on your personal machine. You'd need to do it on your SCF home account if you wanted this stuff to be available in both places. But that's kind of a useful thing to have.
Can I ask you a quick question?
Yeah.
Bash RC file versus a graphical file.
Versus what? Sorry.
So you map your graphical file, you also dash RC, you also dash RC dash profile.
Yeah, I don't actually, off the top of my head, know the distinctions between all of those. But they're all sort of, I think, they serve similar kind of, some of them at least serve similar kinds of purposes of making stuff available whenever you are logging in.
I think the profile file is the default file for Mac.
Is the what?
I think the .profile file is the default bash RC for.
Oh, okay. So that's useful to know. I'm glad you said that. Otherwise, I was sort of giving misleading information. Okay. So you think .profile, you would use .profile on the Mac, and we'd use .bashrc on a Linux machine, on the SCF. Yeah. Right. You definitely use .bashrc on the SCF, but it sounds like .profile is the place to go on your Mac. Okay. So I've already mentioned briefly this idea of having variables and storing information in variables. So I could store, say, the string Chris in a variable called name, and if I do this, then that's going to put it in name. I can recover it by doing echo and see what it looks like. E and V will show basically all of what are called environment variables that are set up on the system. So they're often in capital letters, and these are all the things that are variables that are set up for you as a user that basically control how the system operates. So for example, this has something to do with my default printer. That LP stands for laser printer. I guess this does as well. I'm not sure the distinction between those two. This says what's my login name. This says that I'm set up to use US English as the language, and so on and so forth. So those will sometimes come up. You might need to look at those to see what a setting is for your particular setup. And you can print out individual ones of those in the same way as I just printed out the name one. If you want to basically modify one of these variables and make it available to subsequent commands that get used subsequent to doing this, you often will want to do export. So this will basically, what this does is CD path is basically allows you to when you type CD, suppose you had a file, suppose you had a directory, something like research, and you were doing a lot of stuff with the Bootstrap, and you had a Bootstrap folder in your research directory, Bootstrap. And you got tired of typing CD _ research Bootstrap. Well, the CD path gives you a shortcut that basically says, what this is saying is take whatever the default CD path is, that's this dot, and append to it all these things in each of these pieces in between the colons. So this is appending to it till the research, till the teaching 243. And once I do this, I could just type CD bootstrap and not have to type everything else. I could type CD bootstrap from anywhere. And because research is in my CD path, it will actually go and find and be able to just go to the bootstrap folder that's within research, because it knows to look within each of these directories for when it's doing a CD. So this is a way of basically manipulating this environment variable and adding on to it. Let's see. Right, so what I was saying here about export, the export command ensures that the other shells that are created by the current shell will basically inherit the variable and then that you just either created or modified. Okay. This is a useful one that I use in my .bashrc. You can also put these variable definitions in your bashrc. So you'll notice that whenever I have this formatting that I like that tells me where I am on the system, and it's included in my prompt. And the way that I set that up was by putting this line in my .bashrc file. So if you like that formatting that I have here, you can borrow that and use that in your .bashrc. Okay, so let's talk a little bit about creating a function in Unix. So you can start to see we're sort of building up a whole ability to actually do programming at the level of the shell, and we're not going to go a huge amount down this road, but I'm basically showing you what some of the building blocks are to be able to do a fair amount of useful stuff without becoming expert Unix shell programmers. So we've already seen that there are various kinds of shortcuts. We can create variables. Now we're going to see that we can create functions, and in a minute we're going to see that we can work with for loops. So those are sort of building blocks of most programming languages, including this shell scripting. So here is an example of creating a function that allows me to basically do sort of a shortcut without having to type a lot of stuff in. So something that I often do is I use scp to copy a file from a local machine to my SCF account, to my home directory in my SCF account. But I get kind of I get kind of tired of typing out Pechoric at bilbo.berkeley.edu and then the name of the file. So again, I'm trying to be lazy. So I create a function called put_scf that will put a file on the SCF. And you don't actually need to define what the arguments of this function are. What bash allows you to do is basically refer to whatever arguments are passed in with $ and then the number of the variable that's being passed in. So this refers to the first thing that's passed in. This refers to the second thing that's passed in. And now, if I just create, say, this file.txt, it's just a way to create sort of a dummy file. I can now say put_scf, use this function. The first argument is going to be file.txt, so that's going to get put in here. The second argument is going to be teaching243 garbage.txt. That's going to get put in here. So the result of doing this is going to be copy file.txt from my local machine into my home directory on the SCF, into my home directory teaching243, and then rename it garbage.txt. So that's a pretty simple one, but it illustrates both creating the function and using these sort of anonymous functions that are referred to by number instead of by name. Does that make sense? Any questions or comments about that? Mm-hmm.
It looks like you've used two different ways to define shell variables. Was there any difference?
You mean the capitalization or the non-capitalization or some other?
Earlier you've done files equals $LS in parentheses.
Right, so that was, yeah, when I did that, I can't type anymore apparently. Yeah, so this was basically taking the output from some command and putting it into the variable.
Okay.
If I instead did files equals a.text, b.text, I can create it that way just by directly putting in what I want.
Okay.
So either way, yeah. Okay, so that was an example of creating a function. If I want a function that I create to be available to me, and whenever I open up a terminal window, again, I'm repeating myself here, I need to put it in my .bashrc or in my .profile file so that it's going to be available to me all the time. And so examples of some functions that I have in my particular bashrc, just to save me time, are these various functions here that are shown in the demo file that you could look at just to get some idea of some of other kinds of things that one might create functions with. And you can obviously make you can make functions that are much more complicated that have tens or hundreds of lines of code. These examples just have a few lines. Yeah?
When you use backticks, when you use brackets instead? So when you do files, there were brackets.
Yeah, so that's a good question. I don't know that I have a great answer to that because I think you can do either one in the cases that I've shown you. So if I'm trying to pass output from a operation into a variable, I think either one of these should work. Indeed. If I'm trying to use them as input to a command, we saw something like, where was it here? Yeah, so here we saw that I was using the backticks to pass the output into as an input to another command. So that's a place where we could use backticks. On the other hand, I could probably also do $, and then the parentheses here as well. I think that would also work. So I can't give you a very formal answer, except I think in a lot of cases either one will work. There's probably a subtle or maybe not so subtle distinction that I'm not aware of. Okay, so where was I? Okay, so that was. I'm going to skip over this if-else. And so this is a function that has an if-then-else syntax in it. So again, another aspect of most programming languages is you're allowed to do conditional statements with if and then and else. And you can do that in the shell script as well. I'm going to skip over this and I'll come back to that at the beginning on Monday. And before we finish, I want to talk a little bit about for loops, because for loops you're going to need to use for loops in the problem for the problem set I want. So I want to get started on this now so that if you do want to start working on those problems on the problem set over the weekend and today, that you have that option. So here, let me just give you a couple examples of for loops. So here's an example of doing a for loop where we're basically looping over all of the pieces within a variable. So this sort of goes back to your question. This is saying list out all the files that end in txt, create a variable out of them, use that variable and iterate through each of the elements of the variable that's created. So by default, it's just going to divide them up by spaces. So this should create a variable that's file1.txt space file2.txt file space file3.txt, whatever the names of the files are. When I do for file in that, it should then sequentially pull out each of the individual strings that are separated by spaces. So it's going to individually pull those out, sequentially assign the result to the variable file, and then I've got within my do done syntax, I'm going to do something with that variable file. So in this case, I'm going to move the variable file to a new file, and this is some sort of syntax that we haven't seen before that can be quite useful. This basically says take whatever's in file and replace .txt with .r. So when would this be useful? This would be useful if, for example, somehow or another somebody, either you created or somebody sent you a bunch of R code files, but for some reason they all ended in the extension .txt. And generally we would want to end our R code files with the extension .r, .R. So what this would do is this would sequentially rename each of the files that end in txt, it would rename them as .r instead of .txt, using a for loop to loop through that operation. So this is the sort of thing that you might do a lot from the shell and allow you to automate stuff, where you're just sequentially working through files, doing an individual operation to each file, and then the result is what you were hoping it would be. Any questions about any of that syntax? And we can put more than one line in our for loop. I could have done 3 different things or 8 different things or whatever in there. Okay, so here's another example, playing around with somewhat different syntax just to show you guys examples of some different things that you can do and start to help you build up a vocabulary capabilities of things that you're familiar with and able to do. So here's doing it in a little bit different way. I'm defining this environment variable IFS, which stands for internal field separator, to be a colon. And I said by default before, it's going to, when it does a for loop through a variable, it's going to separate by spaces. But here I'm going to separate by colons. So now I'm going to define in the variable months that is January, February, March, and April separated by colons. And because IFS is set in that way, it's going to know to separate on the colons. So now I'm going to have 2 for loops. One of the for loops uses a syntax different than what we just saw, and one uses the same sort of syntax that we just used. So we can either loop through individual elements of this variable, or I can set up a for loop where I have a variable that does the indexing, and I just iterate through, in this case, YR to stand for year. So what's my goal here? Well, I want to go and download with wget all of the files in this directory on the U.S. National Oceanic and Atmospheric Administration government website, all of the files in this directory that come from the years 1910 to 1920 for the months the months January, February, March, and April. So I need a double for loop because I've got 2 things I need to index and loop over. But this should download 11 times 4 files, 44 different files automatically from that website. So not too much to that. We're referring to the variables by $signs. In some cases, it can be helpful to use these squiggly brackets to sort of make sure that the shell knows exactly where the variable name starts and ends. In other cases, you don't need to do that. It's fine to just do it like that. Any questions about that syntax?
Any restriction for setting the internal field separator?
I imagine there is, but I don't know what it is. There might be some crazy things that you can't use, but I suspect you can use lots of. I suspect you can use sort of standard punctuation and characters. Yeah, Tom.
When you run that code, it downloads those files into the directory that you're in.
Yeah, it's just going to download to whatever your current directory is. Okay, so next Monday we will pick up with wrapping up a little bit on for loops, the if then else syntax, and then we'll launch into Git. So make sure if you do want to try and do stuff on your local machine that you play around with getting Git installed. And as I said earlier on, I'm going to send out a little problem for you guys to work on for Monday, and I'll probably ask a few of you maybe to write up your solution on the board at the start of class. So it's not going to be very formal. It's not, you don't have to turn anything in, but do play around with it and see how far you can get. with it.
Do you have the PDF of this lecture on GitHub?